Hi everybody and welcome to this video. I am Simon alias the Nerd of Algorithms and today is the 20th of September year 2016. Well, here in this video I am going to expose my fifth theorem on polygonal surface approximation. That's the first out of 6 videos expected. Those which I have announced in the video entitled Guide to the Appendix with my 6 theorems on polygonal surface approximation. Very fine. Of course, this video is a little bit particular, not just because clearly I have made decently figures for the thing, and beyond the fact that of course there has been a technological shift in the meantime since the other video which I made practically almost like 1 year ago or what, but of course I hope that you as well have the things as fresh in mind as I do, but if not so, of course I was only joking, we'll take care of the situation. But well, the particular thing is that beyond the fact that I made figures with very much care, this is particular because, this video is particular because it has started first by writing it. And it's not improvised. There will be no waiting time for a transcription into text of it with the figures and whatever. But I've already written most of the things about it, or I'll write them. But let me get more into this. The text is fine. I've already written it in HTML so that it's formatted. It's what needs to be written in italic, like italic text or bold text or whatever, is already done so. But of course, even before I will place this transcription on my website and link that part of it in the official, that article describing introducing to the usage and functioning of these of the new Turing system algorithms, various flavors. I may make the text available in other form, maybe just as pure text, not HTML, because clearly organizing a website is a problem. The most important thing is that the text is there, the video is there, so that one can also have a transcription of it to reread it, or if one has problems understanding spoken English, or maybe is not used to my pronunciation of it, is no problem. In fact, in the text, in this or that way, these figures will be referenced with their true names. That is, if here is figure 2a, it will be written, refer please to figure 2a. Okay? While of course in a full transcription, of course I will put the figures, I may replicate them more times and add arrows to them and so on as to imitate what I can do here in video, that is to show, look, here goes here, this gets copied, that gets added, that is changed, that is not changed. All these fantastic things. And they will have the same names as here, so a transcription will be immediately utilizable. But this is not enough, because as already in that article, as far as I managed to complete it, but whatever, I will use here also secondary figures, of which not these same are on the article, but equivalents. But I have this already here, they have color and everything on the article. Many of these kinds of very simple repetitive figures are made with vector graphics. But here I think that using these won't be confusing. After all, that's it. In the transcription, not the same figures will be featuring, of course, because in a serious HTML transcription I will use a vector graphics, except for complex figures like the one I showed here. These are a bit too complex for vector graphics, and it's also, well, maybe there will be a vector graphics form, but whatever critical. So I think I have introduced, and we can start. Look how much care I took in making all this, because these are my original notes, and these are very, very disorganized. So I think we are making some progress, aren't we? Now, before concluding and starting the explanation, while I show some of these figures, since the creation and testing, showing, and publication of the first prototypes, all written in, not prototypes, but libraries, prototypes, whatever, of the new Turing system algorithms, various flavors, all written, all implemented in the C++ programming language, the very algorithm and the very consideration of, very evaluation of its possible fields of application have gone a long way. And it has proven very good to have made all this effort, because its original aim, that was in some way to try to arrive at an algorithm which eliminates the need to have actually a height map stored as a large file, because it's all made to render large terrains, large surfaces, to make it possible to define, render, and also design surfaces, terrains, whatever, without at all the existence and even consideration of a height map, a height field, in other words, considered in its old-fashioned way, its traditional way, which is correct but not always the best thing, stored as an image file, or just as a text file, but which holds just numbers which are considered to be part of a very, 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 very large big square matrix, because an image instead is a triplet, or just even one singlet. Triplet typically red, blue, green, red, green, blue, whatever color values for this. And well, the objective was to try to invent and develop a whole theoretical framework, which, if we don't want it, we can do everything without having any external file, anything that functions as a height map. And this was succeeded. One can use it or also not. And that thing, that when we decide not to use it, has found an excellent application, something unbelievable before. Also to me, but certainly I show that I have a certain imagination, but not even I thought of it. Yes, it's a browser applications, JavaScript, where accessing external files, opening images, and here and there is not even as far easy and convenient and typical as with the C++ programming language. And yes, it has found an application in that field as meanwhile I started to develop a three-dimensional urban environment renderer, which is called the Felenster City 3D urban environment rendering engine, and also that needs a Theorem module. And what's best for it if not one of the flavors of the new Turing system algorithm set. Well, we are starting from Theorem 5 because it's the one theorem which is at the heart of that flavor, which does not even need, but of course it can still use, any height map, however stored. It uses a sort of internal format of which it's neither correct to say that it's compressed, neither correct to say that it's not compressed. It's sort of file format, which is not a file format. It's a way of defining such a polygonal triangulated surface as it arises from the whole theoretical framework. And since it goes at the heart of the whole idea, whole properties of a triangulated surface, whatever it has been, whatever it's supposed to have been derived from, a real height map sampled with satellites on the Earth, a real map, or a design turning, whatever, it's the whole framework as it goes to the heart of the problem. It offers a true data structure, more technical terms, which allows to operate with it as if it were already in a compressed format, but it's not compressed, not uncompressed, it's that, and it's very simple. And to define even a very, very, very large, complex terrain, we have just a list, a long list of a pair of two numbers, one integer number and one a floating point number, and you know, good, the continuous number stuff, you know, a ratio of two integer numbers, or a real number, call it whatever you like, it's a floating point number. And defining a terrain with this algorithm, it's the specific flavor of the algorithm is the one called the Hight-Data injection enabled new Turing system, and that allows to define very, very complex terrains and load them like this, load them from initial information. Could also be on a file, but whatever, a text file anyway is sufficient. It can reconstruct it very quickly, even because the data that the quantity of the information that needs to, the number of those pairs of numbers that I mentioned before usually are very few, just a few thousand, so that we are the whole thing amounts to a few kilobytes. And yes, it's the most it's a very memory friendly algorithm, and as to its performance, it depends on what one wants to do with it. One can operate static terrains to excellent levels, because even with 3,000 polygons, one can define a very large terrain, which is in some parts of it very detailed, in other parts less detailed, and it allows a lot of freedom in management of the detail. And of course there are all the other things that it can do, the dynamic level of detail, automatic simplification of a surface stored as a height map, and whatever. So let's start from theorem 5. No problem, because to understand it even very well is sufficient to mention a little bit here and there, just hint at the other theorems, not all of them, just theorems 0, which is the set of base definitions and the proof of why they form they are allowed to do something as a theoretical framework. Theorem 2 and theorem 4 and 6. Okay? So that's it. Now don't worry if something is not clear instantly here, because doubts will quickly dissolve as the explanation goes on, and hopefully when I make also the other videos about the other theorems, first of all those that I mentioned, that is 0, 2, 4 and 6, after having gone through the exposition of those as well, you can always come back to this one to really bring the first grasp, first impression of this into a deep understanding. And the other thing is, why theorem 5 first? It's because the only one that has to be understood at some level in order to use with extreme proficiency the algorithm, the Hight-Data injection enabled Newton's system algorithm implemented in JavaScript or C++, to use it with full proficiency. That's pretty all. So we can get started. Cut here. Audio started, video started. We can get started. Okay. Now, as a first step, let's outline our starting point by summarizing a bit the whole theoretical framework on which our terrain or surface approximation and rendering algorithm is based. Very fine. We're going to do this in 4 points. Okay, 4 simple points. So, number 1. Assume we look at the terrain from above down, like this. Okay. So as to consider a 2-dimensional square area. Okay? Overall, something like this. Big square area. Seen from above down. So as to be practically a 2-dimensional, whatever, we'll come to that. Two-dimensional square area. A terrain is a block set. Set of blocks. As stated by theorem 0 on my theorem 0 on a polygonal surface approximation. It's a full coverage, that is voidless, full coverage. Just this. It's a full coverage of a square area, which is our terrain, our surface. This, in the simplest case, is our terrain, our surface. Don't worry about doubts. They'll dissolve in time. A coverage made with smaller square subareas than the original one. Okay, this is the big, and then any coverage of it is made of smaller sub-areas, each of which is still square-shaped. Now, they can't have any side length casually, of course. Theorem 0 requires that the sides of each of the squares
making a fully covering subdivision is so that it can be obtained by halving the side of the big block, enclosing the whole terrain, the whole surface, like just hop, half per side, 3, 2, 1, half it per side, okay, subdivide it, and then by further subdividing others and so on. But so far as we have stated, it's all just a subdivision. We need to be more specific because subdivision in general like this doesn't have any properties. We could go on by subdividing this, 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 and again, and also this. It doesn't have any big deal of qualities. We need to be more specific because we're working on a serious algorithm that has a specific aim to complete a specific task. So, number 2. We are at number 2, okay? We assume that we start from a legal block set. A block set in which a block can be either, sorry if I used a figure, but a block set in which a block can be either half as long per side as one found side at side as the one next to it. Any here, there's nothing but whatever. We could take this also, okay? But it can be also equal, that is so, still fine. Here, take this, these are half as long, so it's all fine. Here, as long per side as it himself. Here there's nothing, so it's all fine. Here the same conditions true, same size, same length per side, same length per side. Here twice as large, here twice as large. Okay, and there are no vertical checks because that's useless because of the fact that this point is shared. That's why we are working with the square system. Operating theorems 4 and 5, my theorems 4 and 5 on a polygonal surface approximation, we can arrive at any desired legal block set. This one is legal, for example, as I try to hint at it. A block set is a subdivision of a big square area. Big square area, we subdivide it. But we also require that it be a legal subdivision according to what Theorem 4 says as legal. Theorem 6 is just an auxiliary helping thing that allows to arrive at any of the possible legal subdivisions of a big square area, okay? So it shouldn't be that difficult to understand. Okay. Number 3, we have now our subdivision, okay, which at the same time is also a legal one. It's a legal block set, according to what I tried to say before, okay. This grants us that it's easy to triangulate the little squares in the subdivision. This is the basic scheme. The one invented by Peter Lindstrom and Valerio Pascucci as well. There is also another figure that I ask you gently to give me the time to retrieve. Okay, adaptive little scheme to triangulate. So that this can be triangulated easily if it's a legal block set and require it to be legal. It's always legal when we start triangulating, or we desire to do so. So we have a fully triangulated Hight-Data when we triangulate this. So Okay, then this goes here, here, whatever. We'll see examples of it later. Let me retrieve the figure. This is an example. Adapt, 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 all simple triangles. Okay? Bam. Don't worry, we'll discuss that figure. This is one of the worst, but whatever. We'll see also examples, but with a computer program implemented, but whatever. Okay. Then we have a fully triangulated hilly terrain, not just a flat coverage of a big square area, as not just as this, but something like this, but with all the triangulations of each one, please, block, so that we have a full triangulated coverage, full thing. Okay. Now, very careful here. As by definition, all surfaces can be approximated by a set of interconnected triangles. Okay, that's not a theorem of mine, that's a basic notion of geometry in general. Two-dimensional and three-dimensional. But we are concerned with surfaces for which it's sufficient to consider everything as if it were seen from above. So it's really easy. Okay, now, operating according to Theorem 0, we go triangulating each block, going from the larger to the smaller blocks. Huh? So, so we go from the larger to the smaller ones. It's all in Theorem 0, so it's not a place to over-explain here, but it's all deterministic. Always the larger blocks adapt to the smaller ones. That's also all Theorem 0, so we are not saying anything so extraordinary. But what about the height of the points that the triangles of a triangulated surface, when we triangulate this, connect? Surely we don't want to continue with a flat surface. Otherwise it would have no use. Well, going from larger blocks to smaller ones, here, this is a scheme of terrain construction, but whatever. This is the base scheme of the. Okay, this is the formula, but let's discuss in the article about this. Now, follow this video instead of going to see that, because this can be understood independently. Okay, what about the height of the points that the triangles connect? Well, going from larger blocks to smaller ones, the larger blocks adapt to smaller ones according to Theorem 0, as I said it before, on each four sides of it. For example, this one. Well, here, this has already adapted. This doesn't have to adapt, But what about this? It has to adapt to this. Here, it doesn't have to adapt. Here, this is as if it didn't exist, because if it's there, it means that already it has been processed so as to make it adapt to this, and so on. On each four sides. If at that specific side of it there are smaller blocks, as I said it before, half as large per side as the larger block itself, it needs to include the point shared by the two blocks at that side. So we need to know this point. So this block, when triangulated, needs to retrieve the height of the shared point, which is this. How does it retrieve it? Well, simply by retrieving the quad-tree ED identification number of this or this block. Clearly, the block from which to retrieve the height information is gotten from the block set vector, whether we choose this or this. Usually it first looks for the lower quid number 1, so first it would search for this in this case of this block. Because 1, 2, 3, 4, these are the parent child enumeration rule, but that's all in theorem 0, that's really just a convention. Okay, it gets it from block set vector. And it's always supposed to be a legal block set, otherwise we wouldn't find this too, or just we couldn't accept just a case of, wow, no smaller blocks are there, or okay. When the block, smaller block with respect to the one that we're triangulating, ED of this is gotten and the block is gotten and all of its informations, the height of the point shared here that we need to know is requested. It's read out from the block's information. The information says it holds to define itself. Okay, it's very easy and fast to do all this because Theorem 2 allows to get the above mentioned quad-tree identification number in a matter of really just a few operations, all done on simple integer numbers. That's it. Yes, it's great, and it does it in constant time, which is proportional to the size, so to speak, of the terrain. The number of those imaginary levels in it, which are shown, is in this figure. Maximum we have like 32 or 64 ones, because, well, try to have a kilometer 32 or 64 times and see into how much little detail it gets. It's proportional to, you can set it to 32 or 64, it won't change. It's practically a constant time operation. Okay, we are at number 4 now of our exposition. Number 4. Okay. Take 3-4 seconds of break. We realize after this explanation, this outline of the previous things, that during the triangulation we don't need to access the height map, because this block, when it needs this height in a scenario similar to the one that I am going to show you now, let me take the paper. Okay. When a block, this larger block, needs to adapt to this, it reads this information, this height information, directly from this one. Okay. So if we see an analogy here, it's the opposite side, left, this is right, but whatever. Every doubt will dissolve slowly as the explanation goes on, so no problem. When this triangulation thing is done, the whole system doesn't need to, the algorithm doesn't need to access the height map that is supposed to be, well, hypothetically there. But we'll get rid of that if it's not needed, but we can also use it. So assuming that there had been a height map, we wouldn't even need to access it in the phase, in the stage of the triangulation. As the triangulation using Theorem 2 operates only on data which were already inserted into the system at some point. This information to create this for blocks has already been inserted, this height into information. for this block to be triangulated, that information would not need to be read again from an external resource. It would be already in the system. In fact, it uses Theorem to retrieve this block or this whatever and get this point and give the same height to this vertex. So according to the triangulation scheme, to make it fully connected. Okay. But during level down operations, that is what I've already shown before, like, okay, use this figure, level down, divide a block into 4, is level down, okay? Level down operation on one block. 1, 2. When Theorem 4 judges it legal to be so in order to arrive always from a legal block set to a legal block set. Now hold tight for some moments more. As we go on constructing a terrain, as here, we construct it, it comes out that we just need to access the height map's same points more than once, because even if the triangulation doesn't require to access it more than once, the triangulation, as I said, doesn't even require it, but before it had to be accessed, well, during these operations between this and this and this, always during between two stages of which include a level down operation, the height map needs to be accessed and may have to be accessed. The same point of the height map may be needed to be accessed more than once. And theoretically, that's not too nice, as a really good algorithm should be able to reutilize data which have already been inserted, injected, as we'll refer to this later, into it at some point. Would it then be possible to develop a procedure to allow constructing a terrain by accessing only once each of those points of the height map which we decide to use? Well, Theorem 5 defines that this is possible. And, okay. And says how. In essence, it relies on a more advanced use of Theorem 2 than the triangulation stuff alone does. And since each used point of the height map needs to be accessed only once, that hypothetical height map can be clearly replaced by a simple data stream. A sequence of floating point numbers representing height values injected at each stage of a set of level down operations. And the data stream can be random, can be semi-random, or inserted by a human being who wants to use a system to design easily a terrain, a height field, but seen in a more modern perspective than the old-fashioned height map intended as a square image holding color values which represent height values as they are. And okay, we can get started and expose Theorem 5. End of scene. 2. Cut here. Very fine. We are at stage 3, where we'll prove the theorem as something from which also other facts very important to know about the whole Hight-Data injection Newton system algorithm will come out. So let's get started. At this point, since I discovered this thing, I developed it, I think I managed to explain it really simply so that anyone who has come from you, dear listeners, so far in this video explanation should be able to understand at a basic or advanced level what is going to be said in this last stage of this video exposition. Very fine. A basic understanding is sufficient, of course, for usage in general of this thing, which is anyway. Let me take a moment, please, because basic understanding is perfectly fine for usage of this thing, but an advanced deep understanding for those who can achieve to acquire it is good for those who want to make very advanced usage of the system or are interested in exploring new frontiers of it, for example in medical imaging, civil engineering stuff, clearly video games, scientific visualization, and whatnot. So let's get started. I said that I would show the system at work, but before doing it, let's outline what's the point, what is going to be what I'll show. Now consider the basic scheme, basic outline of the proof of the theorem. Our lemma, our starting point, is that we respect all requirements set down by Theorem 0. Our hypothesis is that we start from a legal block set as defined by Theorem 0 and consider level down operations judged legal by Theorem 4. We'll come to that. Here the thesis comes, what we want to assert, but I wrote it on a different page because it was a bit easier so. The thesis essentially is that a terrain, a surface, corresponds to a simple data stream made of integer and floating point numbers in a sequence whose structure is schematized as here. A moment, please. Just here. It's made of chunks of sequences where, very important, why chunks? Because Theorem 4 says that at a certain block set, not all blocks are eligible for level down. Not all of them. Which are eligible are those which the Theorem 4 says to be eligible for a level down operation. Now, which are these chunks? Chunk 1, chunk 2, chunk 3. But it's still a data stream, so we just need a separation between them. But it's a data stream, an integer number, which says which says the QED number, the quad-tree identification number of the block to level down, and then says which are the Hight-Data which need to be injected. Not every detail to know about Hight-Data injection will become clear through the proof. Okay, very simple. It's just made of integer numbers, but floating point numbers, continuous numbers, call them whatever you want to call them. It's real numbers, rational numbers, whatever. So what the theorem asserts, what's the thesis, and more mathematical terms, even if this is algorithmics, but whatever. It's a data stream from which the terrain can be reconstructed in a matter of a few seconds on a modern computing system. As there's, in the context of the Hight-Data injection Newtonian system algorithm, a biunivocous correspondence between the terrain and the data stream. There's a terrain and a data stream to which the terrain was, so to speak, converted or downgraded to whatever level of precision, faithfulness to the original, and it can be reconstructed. Now, clearly a terrain can be handcrafted also, or generated in a semi-random way. That's, I'll show to you on the computer what that looks like. And clearly it can be based on a height map, which is analyzed and downgraded, so to speak, using Theorem 3, my Theorem 3 on polygonal surface approximation, well, to whatever precision. So we have height map, we can do that so-called pre-simplification process, downgraded. Maybe no information is lost, but that's when I'll outline Theorem 3, we will come to it. Downgraded, maybe just intend downgrade in a non-pejorative way, and then we have our data stream constructed. Well, it has chunks, sorry, I made a mistake in the figure. There are these chunks, sequence of chunks of data sequences, whatever. And then this defines the terrain, and from the terrain, well, every terrain can be converted into a data stream of this kind. That's essentially the thing. Okay, let's get started. Remember just that the chunks are this. One here, here. No. First step of the proof of the theorem. Moment, please. Okay. Everything recording, fine. Proof. We define the level down operation with Hight-Data injection, first assuming one single level down per step. One of those steps, which are one step of the base algorithm, is by Theorem 0. We obtain that then there are two possible scenarios, cases A and B, of a schematization, cases A and B of this scheme. We rule out any complication with corner points. We'll come back to this. The two cases are from this, which we assume to be legal to level down. We pass this. We assume that here, 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 there are blocks of the same size. Let's try to let it intend, but well, should have put also a line here. So, okay, also here. So we can do the level down, and this already has to have has to have head injected into it, a height for the central point, and when we level down it, it's just simply a question of copying it. Hop! You can visualize it also so. One, please. So, one, inject. So are injected 4 points here plus 4 for the center. 1, 2, 3, 4. Effect. 8 height points are injected. Whatever. Then we go to figure 2, case 2, when we have some more complicated adaptation. What if we want to level down this? Okay, see what's copied, what's injected. This is copied. Injected, injected, injected. The other 4 center points here, 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 here are injected, but that's pretty trivial. The central point is copied because it used to be there already. That's why we need always to inject also one, even if it may happen that it never comes apparent, but it's not all that important. So here, and see the sequence, the arrows with the camera. Okay, these two are copied. Okay, I hope you could acquire this. Well, I do another superposition. 1, 2. Okay, so cases A and B of the first line, one level down per step, is possible and works. The purpose of the proof, in fact, is to prove that the method is possible, say why it is possible, and say how it works, what is going on, in fact. After having said what I said before, we rule out any complication with corner points as they become available always as the terrain is constructed by level down operations, starting with the root block. An hypothetical construction scheme, which is clearly this. The corner points become available. Always convince yourself, in fact, if we see this scheme, we have that these corner points are always there, those which need to be there, clearly. Okay. This scheme here replicates this situation, this lower part of this. It always works because we start from here, 4 corner points become available, then this corner points, and so, and we arrive always having the corner points ready for those cases in which Theorem 4 judges legal to perform a level down operation on a given block. Okay, this is a scheme. Try to do something. With the root block, the case is trivial. As I stated, we require the root block to have already 4 corner points. And it needs to be injected to it 1 height point here when it's level down. 1 here, 1 here, 1 here, 1 here. Stop. And also this. Hop, 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 hop. So that's it. We're fine. Now let's go on. All doubts should dissolve because you can always revise this slowly. So this is a scheme. Root block, level down, the first level down. We inject the points. We inject the central point. So there are 5 things. We have new corner points available. the already existing ones, this, plus the other 5 that we injected. And so we can go on with other level downs, and the corner points are always available for those blocks which Theorem 4 judges judges eligible for level down operation. It works. Okay, fine. The only thing remaining is to prove that multiple level downs per step are possible, still maintaining determinism of the system and functionality. So we go to point B to do it. Multiple level downs. Here you could see that we did multiple level downs, here to here, this to this, and we could have done also more, but only on those which Theorem 4 judges eligible for level down. What happens? How does it work? Does it work? Why does it work? We analyze all the cases of a moment please, of line 2 of our scheme. We have case A, B, and C. About the root block creation we have already spoken actually, so that's not all that big deal. But this is already ruled out. We have this. We go from the first level down stuff of the root block to have 4 other blocks, and now we move on from this and we try to define what happens when we have the total general multiple level down thing. Okay, so let's get to figure 3. Figure 3, 4, and 5 will help us. This is an example of case A of multiple level downs. Theorem 4 is being used to check it all if it's legal. Okay, no Hight-Data need to be propagated, no copying actually is made, because these are never the blocks that we scheduled for level down are never found side by side next to each other, and so all height information is just injected. It's an easy case. There is no propagation, no overwriting anything. Just look at this scheme. It's not beautiful, but okay, this is a lower right corner of the turn, so imagine it's so. Okay, lower right corner, this here. Figure 4, what's in case B? What's case B? A more difficult case when something may get copied instead of being injected, or it's whatever. This is an example of multiple level downs performed in one step, but where there is a mix of copying Hight-Data and injecting. Look at the scheme and convince yourself that also this is well defined. I did a little variation here with respect to the previous figure, so don't get confused. You can confront the two cases A, which is easy. We see this diagonal disposition of things, while here we see a more bad thing, because here there are blocks of the same size as this block when it's the level down is being done. So a copying is needed here, copying is needed here, but it works. Because thanks to Theorem 2, this goes, retrieves the Hight-Data, copies it, and where there's no copy, it injects it, and injects also always these 4 central points. Well, we are now at figure 5. What happens in the totally general case? You must prove that it works. when we have something like this, we want to level down 2 blocks, but of which, well, before they used to be of the same size. Is it possible? What goes on? Some overwriting is needed because here it's injected, here then it's copied. As to theorem 0, we always go with the level down scheduled and judged legal by theorem 4. That is all scheduled level downs because we schedule only the legal ones. How is there is an overwriting procedure. If this as a random stream, some overwriting is needed. Does it work in the general case? Does it propagate so as to make a pure situation? Yes, and we are to prove this. Look, since everything is sorted according to theorem 0, according to the QE number of each block, the level downs happen from the lower QE blocks to the higher QE ones. And as this is already leveled down, we level down this, and since this point is already here, and these two blocks run, and this corner is retrieved with theorem 2, this is overwritten. And then here we have something beautiful. This is the extreme case, as a line extracted from this. The general case is this. I didn't have time to make the figure, but look how it gets propagated. The order is block 13, 14, 16, 17, 18, 19, and whatever. There is a going through of the thing which is deterministic. And we are almost at the end of the proof. We are proving this. Everything else is done. Start here. Start. We go to the possibility to do multiple level downs, and if we want to do them, wow, we show this can be done. This is the only one missing. What happens? This. Look how the overwriting system manages to give us something that works. Hope all done well. We have a data stream, but some overwriting is happens, halving the population of the injected data in those cases in which there is this kind of situation. And then we have an essential stream, that what remains after the copying things. Okay. So, well, that's a static set. Same data stream builds the same terrain, and it works. It is this we could call a sort of adaptation cascade, and is deterministic in its result because Hight-Data are injected first lower QED blocks, so lower QEDs win, so to speak, in the determination of the final shape of the terrain. So we are virtually operating on a static set. In fact, dynamic sets are risky and hard to work with in general. And so the last point remains to prove here that we have a data stream of the above defined kind, and it's univocally corresponds to a terrain with the Hight-Data injection enable new terrain systems contexts, and vice versa. So as a last, we can state that, wow, what was in the text is given data stream of the above outlined kind, this leads to a terrain, and vice versa, as we wanted to prove.